Hello and welcome back to a new video, D3D12 here on the Ludwig Fussel channel. Now in this newer, modern D3D12 video series, we're gonna try to do an ad hoc approach on DirectX 12, so basically everything hands-on, most of the time just code and just explaining what we need. However, we are now at a certain stage where I can no longer completely hold this up without doing some theoretical stuff. And the theoretical stuff that I want to do is going to be today, because today we're going to take a look at the rendering pipeline, or the graphics pipeline, however you want to call it. Now, I try to stay away from these theoretical things as far as possible, and just explaining them if you need them, explain them on the code, explain them on current examples without overloading your brain too much with the complications that are going on here. However, now that we have talked a bit about the basic concepts and that we are now going to go into the phase of actually building a so-called pipeline state, we actually need to understand the graphics pipeline. This is now really important because, well, this is what the GPU is doing. The pipeline, this is how all DirectX 12 calls are handled with the pipeline. And if you don't know what it is and what it does, you cannot fill out these structs and create yourself a pipeline state correctly. You need to know how it works, and even if you know how it works, it's probably going to fail, and you need to go to debugging and see what went wrong. But in general, for very, very simple start, we want to go into and we want to take a look on how rendering works and how the pipeline works. Now I've opened up a bigger image of that so that you can see it a bit better. Now this image describes the DirectX 12 graphics pipeline, or rendering pipeline, however you want to call it. Rendering pipeline is more like the pipeline of your application. The graphics pipeline, it is kind of like how DirectX 12 does that, but really doesn't matter. It's just a term. Now this is the work that the GPU is doing. Every call that you're doing on your command list, every draw call, is gonna invoke execution of that rendering pipeline. Now the rendering pipeline itself, it's not the whole image, it's actually just everything inside of that kind of like black tube here. So the input assembler, vertex shader, hull shader, tessellator, domain shader, geometry shader, rasterizer, pixel shader, and output merger. These are the parts of the rendering pipeline. Everything else is just there to support the rendering pipeline. Now, to understand that a bit better, I want to kind of like quickly go into what the input assembler is and what the output merger is, and first explain these two, even though they are like at the top and at the bottom, because we already talked about these in some certain extent. And then if we are knowing what the input assembler and output merger are, we then can kind of like take a look on what is required in between and what is optional in between and why it's optional, and how we can kind of like abuse all of these things to get a output result that we want. Now let's start at the output, because this is the most common one that we already talked about. Now the output merger is the part of the rendering pipeline that takes generated pixel data by the pipeline. So at some point we want to output to a screen. So at some point we're going to have a set of pixels that are emitted, in this case from the pixel shader. I'm going to go to that later. And what the output merger then needs to do, it needs to merge this pixel data onto our buffer. And this is why we have the output merger here. Now in general, what we have done with our output merger already is we have kind of like bind this render target. If we're taking a look at our code, you can see that we had called the function om_set_render_target. Om stands for output merger, and set_render_target means basically setting, or set_render_targets means setting the render targets. In this case, we had one render target and no depth stencil there. And this is basically then bound to the output merger. And what the output merger does is, as soon as it gets a pixel, it merges it onto the render target. Now the render target is described by the render target view, or multiple views, depending on where you want to merge that. You can actually render to multiple things in one go. And it can do this in combination with the depth stencil view. The depth stencil view is kind of like an additional test that indicates if a pixel should be positioned on the render target or not, or how it should be positioned to the render target, and many things like that. Additionally, the output merger itself also has many configuration parameters, for example, blending. So if there is already some content on the render target, how do these two pieces of content get blended together? Do I just take the new pixel and overwrite it? Do I calculate them in a certain way? Do I replace them? Do I take the one that's on the screen? How do I do it in combination with this so-called depth stencil view, or not depth stencil, with the so-called depth stencil? And this is kind of like all done by the output merger. So the output merger is kind of like the bottom of the pipeline that takes all the generated data of your one single rendering go and merges it onto the data of the existing rendering go. So in general, you're gonna have multiple kind of like draw calls. If you, for example, render terrain in a certain way in your engine, then first terrain is rendered, merged on the depth stencil view. Then maybe some normal objects are rendered on the screen, are merged on there. Then some transparent objects are rendered and merged on there. And then you maybe also render the character and merge it on the screen. And maybe you need to do other operations. However, this is not a good design that I just suggested. Maybe there's one big rule that says every object needs to be rendered and then all the transparent objects, but it's a different story. It's just like that you understand how it works. You're going to have multiple sets of these configured or specially configured goes of the rendering pipeline. You're going to have multiple ways of executing them, multiple parts enabled, multiple parts not enabled, different support structure on the left, different support structure on the right, maybe. And you're going to have multiple of these configurations. And at the end, they all need to be merged on one single resource. And the output merger is the part that handles that. And that's really important to understand. I'm saying that because many problems exist because the output merger is configured not correctly. You can have everything configured, all your shaders written correctly, and everything is okay, but you forgot one single configuration bit of the output merger, and you're not going to get an output. And that's really important to understand because this can take and give you a bit of a headache. This is a big source of error, the output merger and how it's configured with its views. However, in general, it's actually quite simple. The most simple way to configure it is basically put the pixel that has been produced on the render target. And that's basically how we want to configure it as well. Not today, not tomorrow, but in the future, because we're going to start at the input assembler. Now, talking about the input assembler. The input assembler is responsible for taking all that support data that should be drawn on the screen. For example, like a cube or triangle or whatever you want to render, a character, a terrain, a glass window, whatever you kind of like want to render. It is taken by the input assembler. The input assembler has a configuration, for example, the layout of the data, how are the geometry data laid out, how are the parameters of the layout, where is the layout located, is indexing used or not. Many important things are taken into consideration by the input assembler, including like drawing points, lines, or triangles. And what the input assembler does, it is kind of like taking all the data from the right memory locations with the kind of like right layout, and it puts it into a format that it can be passed through the rendering pipeline. So in general, vertex buffer views, we're going to get to them in the details, and index buffer views are kind of like a support structure that describe how, or not how, but where your data is located in memory, and then the input assembler takes some additional configuration data, how your data shall look like, and then it takes multiple of these vertex buffer views and one index buffer view potentially, and it generates a so-called vertex stream or vertices in general. So in general, everything that's handled in this stage of the rendering pipeline is a so-called vertex. A vertex is kind of like a single point on the screen, and the vertex can either as a single vertex define a point, which is then rendered if the pipeline is correctly configured for point rendering. If it's configured for line rendering, you need two vertices to render a line. So you basically define the two edges of the line, and then subsequent parts will render a line between these two vertices, or in the mode where we're gonna abuse the GPU like 99% of the time, it is gonna be in triangle mode. And if it is in triangle mode, it basically means that we have three vertices positioned somewhere in three-dimensional space or two-dimensional space, depending on what you want to do. And these three vertices make up one triangle. And it's the job of the input assembler to be configured in the right way, to kind of like emit the right primitives, so the right vertices linked together in the right way with the right data from the right locations in the memory. This is kind of like what's done by the input assembler, and that's emitted by the input assembler as single vertices with a bit of logic behind them on how they are kind of like connected together. Now, this is kind of like the top and the bottom that we have. Down here, we have kind of like a discrete image. We have an image that's defined by a certain width and height, and kind of like, yeah, width and height. That's actually the most thing that we have there. And this is basically how we define like that the output of the pipeline. The output needs to go onto that image, and the input is some arbitrary point, line, or triangle set. And I really say arbitrary. You can define whatever you want. You can define your own layout. You don't even need a position or three-dimensional position in space. However, it is highly recommended that you do, because at some point you will need a position, or if you don't have a position, it can be placed somewhere on the screen. Talking about these placements and how it works, let's now take a look on how a triangle, I'm now going to, for simplification, use the term triangle, how the triangle is going to go from the input assembler to the output merger and which steps it needs to go through. Now, in general, it is quite easy. It just needs to go through these, not all of these purple ones, and this like darker blue one. Now, in general, the input assembler produces vertices. So in case of a triangle, 3 vertices. Now these vertices are in any arbitrary format, and to be able to take this arbitrary format and to convert it into a format that the GPU can understand, we need to transform each single vertex into a kind of like different format. It's not 100% required. At some stages you might even have it in the right format and it can just be passed through. However, we have the option to transform them. How do we all have the option? Why don't we say we're just going to input them into the right format? Well, because we want to render arbitrary things. For example, in a game you might have a bottle that the player can throw, and this bottle might be positioned into several locations on the screen. For example, if you have a crate with like 10 bottles in here and 1 bottle in the hand of the character, you need to draw this one single bottom 11 times. And thus you need to be able to modify the position of that bottle. So the initial data that's stored somewhere on disk and loaded by your engine. In general, it just describes how the bottle is laid out, centered at the origin. 3-dimensional coordinates, how your bottle is centered at the origin. And this data, this bottle centered at the origin, is then assembled together by the input assembler into triangles and then passed to the vertex shader. And now in the vertex shader, you would have all of these bottles at the same location. So what you do in the vertex shader is you take that bottle, which is currently centered at the origin, you move it into to the position of the world, so kind of like where is it located in the world, and then when it is at the world position, you need to take into account the player's position, so how is the player camera orientated, then you kind of like move the bottle into the orientation on how it would kind of like be taking the camera position into account, and then you do some additional transforming, and they're called something called like projection, which takes the 3-dimensional coordinates and project them onto a 2-dimensional surface, in this case our screen, and then we kind of like have done what the vertex shader shall do. We have some ready vertices now, some ready, let's stay at the term triangle, that's positioned correctly on the screen now, in terms of like coordinates, 3-dimensional coordinates, and that now can be converted to pixels. And that's actually everything that we need to do. All subsequent stages like hull shader, tessellator, domain shader, and geometry shader are fully optional. We can opt in to skip all of these 4. So we can directly continue on to the rasterizer. Now the rasterizer is a fixed function but configurable piece of hardware on the GPU, and it is there for taking a triangle and converting it into pixels. So it's taking the triangle's position by some parameters. You basically tell it how big your output image is. You tell the rasterizer how your so-called viewport is laid out, so how values shall be interpreted, something like that, a few additional configuration parameters, and then what it's going to do, it's going to take these 3 vertices. It is going to compute the area that the vertices are covering, and from that area it is going to output all the pixels that are covered by the triangle. It does an additional thing. I told you that the vertices can have any arbitrary layout in terms of data, like positions, maybe color data, texture coordinates, whatever you're going to have there. You can have an arbitrary layout that you have here, and this arbitrary layout needs to be passed on to the pixels because, well, the pixels are born kind of like from vertices, so they also need to have the same attributes like vertices so that you can kind of like continue on and also compute data on a per pixel base. So what the rasterizer is already also doing, it is interpolating the three data values from the vertices into the data values for the pixels. It's called a bicentric system of order 3. Or trilinear interpolation. So it's taking kind of like every vertex is of course the same. It's kind of like taking the position of all of these three vertices. It knows how far the pixel is kind of like away from each of these vertices, and then it can kind of like interpolate these three values into one dedicated value for that pixel. And it's doing this with all data you're going to give it. If you're later on going to give it texture coordinates, no problem. They're going to be interpolated. If you give it color values, they get interpolated. It's always an interpolation. You can tell it to not do the interpolation. If it's not doing that, kind of like assumes that the color are the same or the data is the same for each kind of like vertex data set, and then it can also skip that interpolation. However, in general, it interpolates all the data, and then from the rasterizer on, it outputs pixels. Now, in general, what we have done, we have inputted one triangle into the rasterizer, and now we get a variable amount of pixels out of the rasterizer. This definitely depends on what happened to the triangle. If the triangle is quite small, the number of pixels are quite small. If the triangle is big, the number of pixels is big. But at the end, you're going to have pixels that are kind of like put it out from the rasterizer. Now, what you then do with the pixels, or what the graphics card is doing with the pixels now, is it is outputting them to the subsequent stages of the rendering pipeline. However, the pixel shader here, the next stage that we would have, even though many people don't know that this is actually an optional stage. You can already have all data that is required for the output merger to actually put color on our buffer, so kind of like called the target value. This can already be assigned by the vertex shader. The vertex shader or even the input assembler could already define the target color of a per vertex base. So for example, a triangle, you're going to define the color of each edge of the triangle. The rasterizer is going to convert this into pixels. The color is going to be interpolated. The pixel shader doesn't need to be there. And there's enough data for the output merger to output the data on the screen. Now, this is kind of like the most simple flow that we have. However, that flow is never gonna be there. We're always gonna have at least the pixel shader in there. The pixel shader, it is a certain piece of software, so it's code on the GPU, a shader, code on the GPU, similar to the vertex shader, that has the option to transform the data produced by the rasterizer. So in general, this is going to be just one function that is going to be called in a certain language called HLSL, very similar to C/C++. It's kind of like an intermediate between C and C++, if you would ask me. Not really object-orientated, but still it is, and not really supporting templates, but sometimes it suggests it does. It is kind of like C++, but not really. Now the language HLSL, it is you're going to write a function in HLSL. The input is going to be a vertex, in this case after the rasterizer, because the layout that has been kind of like approached by the input assembler or output of the vertex shader or any other stages, it is kind of like in the format of a vertex, but then like each triangle, so three vertices are kind of like getting interpolated into a set of pixels, but the format is still going to be the same format than like the vertices, and then it's kind of like fed into the pixel shader, and the output of the pixel shader could be, and that's a very important thing, could be completely different and will be completely different to basically reflect what data needs to be put on our render target or render targets or dev stencils, and how this all shall go together. So in general, rasterizer, it's going to output pixels. The pixels are going to still have the same data than the vertices, and the pixel shader then has the option to transform them. For example, speaking about or rendering beautiful graphics, your geometry is not colored. Your geometry just contains like hints, meta information on how the color shall be filled in. The color is then done by the pixel shader. In every stage before rasterizing, you're probably going to have something called a texture coordinate or UV coordinates, and these texture coordinates are used to look up the right pixel values in a texture using normalized coordinates from 0 to 1. And basically these input data getting interpolated by the rasterizer, so the actual texture coordinates getting interpolated themselves. And then the pixel shader can do a lookup in the texture using these interpolated values on a per pixel base to then get actually a color that can be merged onto the screen using the output merger. So this is kind of like the pixel shader. Get the data get the data of the vertices that are now interpolated to on a per pixel base, find a color for them, merge them. That's kind of like the idea here. Above here, it is all a bit harder. Now, we already talked about the vertex shader. Now, the vertex shader, its sole purpose is taking the kind of like general input from the model, so for example centered at the origin or generated by the CPU at a certain position. It's kind of like taking all of these general parameters, these most generalized things, to kind of like not ship a 3-dimensional model per bottle that's instantiated in a game, just one time the bottle, every resource just once, and then kind of like instantiate them by kind of like modifying its position. It's kind of like the purpose of the vertex shader is take the current situation of the engine into account to position the resource correctly. Now, that's kind of like the vertex shader. Now, the vertex shader, again, it emits vertices. Now, these vertices can now flow through these 4 subsequent stages that we have and have not discussed. Now, let's quickly talk about the geometry shader because it is simple. The geometry shader has the potential to generate new geometry data. This is why it's called geometry shader, or to remove geometry data, or to alter the topology of geometry data. So in general, the vertex shader, it is kind of like processing vertices individually, but still kind of like of the context of a triangle, or let's in this case, for this example, say point. So let's say we have a set of 10 points. These 10 points are fed into the vertex shader. They are positioned somewhere on the screen, and then they are spilled out to the geometry shader. Now, what the geometry shader can do, it can take these points and kind of like convert these points into triangles. So what it could do, it could take one point and create a quadrat out of that by basically creating 4 new vertices combined to 2 triangles. This is kind of like the idea of the geometry shader. It takes an input set of primitives, or an input primitive, and produces a set of primitives. So it kind of like increases the order. This would, for example, allow for drawing UI elements with points. So you always define the top left corner of every UI element that you want to draw on the screen, and then the geometry shader can kind of like expand that to the actual area that's required. Or also for line drawing. If you want to do line drawing in general, if you render line drawing by defining a proper line, a line on the DirectX 12 meaning, so 2 vertices connected together. If you do that, you're always gonna get a very, very thin line that you might not even see. So a line that's basically just gonna cover 1 pixel. And if you then, instead of like these 1 pixel lines, have a bit of more area to that, you can take like this line into the geometry shader and again produce 2 triangles that can then be properly seen on the screen with a proper like width of the line, for example. Just one thing on how you could do that. Now, the geometry shader is kind of like the father of these 3 other stages, because what people have done in the geometry shader is they have used the geometry shader for something called tessellation. Now, the idea of tessellation is that you are taking a primitive, for example a quad or a triangle, and you split it up into multiple primitives. So if you have a triangle, you can easily kind of like on every half of the lines connecting the vertices of the triangle, you can create a new vertice, and then out of 1 triangle you can create 4 triangles to kind of like increase the order. And if you have 4 triangles, you're gonna have more details. This is a common way of rendering stuff, for example like UI and not UI, sorry, terrain. Rendering like terrain with tessellation is because you basically just kind of like define a very, very simple like control patch. You define a parametric function that kind of like defines the terrain for that certain terrain patch. And instead of really storing the terrain in a very high resolution data, you kind of like store every tile of your terrain in like let's say 4 points, right? You have 4 points. These are kind of like defining your terrain, and it's not very fine graded. And then what you can do in like tessellation is you can kind of like split up this patch of like 4 points of a quad. You can take this quad, you can split it up in tessellation into multiple subquads, or actually most of the time triangles, because you're on the GPU. And if you have splitted them up into kind of like a higher order, you can then take into account the parametric function or like a height map texture that you have, which is kind of like defining how high your terrain shall be. And then you can kind of like dynamically adjust these new generated points to different heights than the 4 original points. That is kind of like the idea of tessellation. And this has been done in a geometry shader, but the problem is that the geometry shader is code, and it actually does take quite a lot of code to generate like new vertices, to generate new connections between the vertices. You need to kind of like imply a certain order so that it is linked correctly together. It has to be a certain property, and it's quite a lot of work and a lot of code and a lot of heat that the GPU needs to generate to do this with the geometry shader. And this is why they have invented dedicated hardware for doing these kind of jobs, the so-called tessellator. The tessellator's job is just to take kind of like let's say a quad patch. It's always called patch on the tessellator, and it's just used to kind of like feed in this quad, tell it on which edge it shall subdivide this how many times, and then it's kind of like following a certain algorithm internally built into the hardware that is then very fast and efficiently doing that without having to execute code that's basically saying, all right, take that coordinate, add the following value, add the following value. No, it is basically doing all of that in hardware. And combined with the tessellator, we have the hull and the domain shader. The hull shader basically takes like the output data from the vertex shader. So the vertex shader basically or could kind of like have positioned the terrain patch somewhere in this three-dimensional world, and then the hull shader can go in and actually now parameterize how tessellation shall go on. So it kind of like defines, all right, I want to subdivide this that many times, this is how the algorithm shall work, etc. Then the hull shader feeds in the tessellator creates new vertices and connects them kind of like together to triangles, and then we have the domain shader to now actually apply all of our modifications, because, well, the hull shader defined how we tessellated that. The tessellator did do the tessellation, however, the tessellation that now has been done doesn't really look nice. It's still flat. It is not different to what has been there before. It's still the same, just a higher order, and then the domain shader can go in and modify the data so that it actually looks different, and then it passes on through the rest of the pipeline. And I think you can even like change the geometry shader in there as well. So after the domain shader produces data, you can still add the geometry shader if you want. And then it still follows the same kind of like order than everything else. And if you kind of like paid attention now, if you're defining the borders correctly, so if you have a strict API of the pixel shader, a strict API of your tessellation stage, a strict API of your geometry stage, and a strict API of your vertex stage, you can actually reuse that. You can use the same pixel shader, and most of the time you're going to use the same pixel shader for most of your rendering work, especially if you want to render like opaque geometry. There might be tessellated geometry, there might be non-tessellated geometries, but they're going to use the same pixel shader, because the pixel shader is still the same. It's still the same. It should still look the same, even through the order by some certain way has been adapted above here. And that's actually like the power of the graphics pipeline here. Now, as you can see, the graphics pipeline, and especially like these programmable shaders, they're getting some data from the left. We haven't talked about that data yet, and I don't want to go into too much details because we're going to get to that in the future as well, but I want to quickly explain the concept of what we are doing there on the left. Now, in general, all of these shaders are just pieces of code that can just work with the data they are getting from the stages above, and they can only produce the data that is kind of like below. So kind of like you need to follow that flow. However, as I told you, the pixel shader might actually need to take a look at the texture and need to actually load color information from the texture, which is somewhere in memory, to define its output values. So additionally to the data it gets from the rasterizer, it needs to get data from memory. Also the vertex shader, if it transforms an object to a certain position, it needs more information in how the object is looking. It needs the information on where the player is positioned, what the properties of the camera are, and where the object is placed. It needs all of that meta information. All of that meta information is of course somewhere stored in VRAM on the GPU. And to access all of these data, no matter from which shader, they have extracted this into the concept of root arguments and static samplers and descriptors and madness. Let's quickly talk about the madness and how we access that. In general, what you're going to put into each shader is a so-called root signature, and this root signature is composed out of root arguments. Now, root arguments are in general just a set of kind of like descriptors or data information on how something is accessed. For example, what you can do is you can just put in some constant data on the root signature. On the root signature, I can just basically say, all right, I'm just going to put a 32-bit constant in here that describes stuff. So that is something that's possible here. What you can also do is you can say, all right, I want to actually describe access to a resource. So you can actually put a descriptor on the root signature. The root signature is small, so it's not really a good idea to put many descriptors on there, but if you have a simple descriptor, you can put it on the root signature. Now, if you have a bit more data that you want to add to the root signature, you need to put in some so-called descriptor tables. There are two types of descriptor tables you can put on there. There is a way to put in a descriptor table for resource views, and there's a way to put in descriptors, or not actually even descriptors, but actual samplers themselves in these tables. Now, in general, a descriptor table is basically just a descriptor heap. We already talked about these, and the table is kind of like defining how the data on the heap is laid out. For example, what descriptor of that type, then a descriptor of the next type, and then 5 descriptors of the third type. The types that are available are actually here on the left: SRV, UAV, and CBV, so shader resource view, unordered access view, and constant buffer views. Now, in general, they are used to describe access to resources. For example, how does a texture look like? How is the width and height of the texture? How is the format of the texture? Or, for example, if we're talking about raw data, what is the stride of the data, where it is located in memory, and parameters like that. So in general, shader resource views, constant buffer views, and unordered access views are views that kind of like describe where a resource is kind of like located in memory and how it is laid out. And with these meta information that are stored in these descriptor tables, where it is located and how it is laid out, our shaders have the opportunity to access the GPU's memory at the right position and read the data. Now, this works for normal data. However, for samplers, it is not that, or for textures, for images, it's not that simple, because images might need to have interpolation going on there. Because in general, I told you that textures are accessed via texture coordinates that are interpolated by the rasterizer, and these texture coordinates are normalized into the space of like 0 to 1. However, 0 to 1 does not map onto a pixel texture. 0 to 1 maps to 0 to 1 and not to width and height. And this is why we need the sampler. The sampler's responsibility is to take the metadata from the shader resource view, so the actual view that tells the GPU how the texture is laid out, how wide it is, which format. It basically takes this information, the sampler, and it takes some additional configuration parameters to take these normalized 0 to 1 values and convert them to actual pixel value. And actually, it might even not be 1 pixel value. If it is between 2 pixels, it might actually do some interpolation between these 2 pixels from the texture again. So there's a hell of a lot of interpolation going on the GPU, and to correctly define these accesses and to correctly define it also if we don't want to have interpolation, for example, or if we want to have special interpolation, like anisotropic filtering, how it's called, for example, then we need to describe these in a sampler. And we have two ways of doing that. There's one way of doing it in a static sampler. The static sampler is directly written in the root signature, but does not count as a root argument. It's basically just a kind of like preset of a sampler that's compiled with the shader. It can then be at runtime restored. So at runtime, when the shader is loaded, the static sampler is kind of like detected, and its state is kind of like restored on the GPU. So this is kind of like a way of doing it. However, there might also be samplers that we want to configure at runtime. So we might have kind of like one sampler that's there for sampling all of like our three-dimensional object, and depending on the settings of the user, we might do finer sampling or harsher sampling. So we can then kind of like define the descriptor of that sampler on a descriptor heap, and if we do that, we need to kind of like reference that via the descriptor table, so that we can properly access the data here. So many things that need to come together to do all of that. I didn't want to make the video that long. However, I hope it wasn't too boring and you have a bit of an information and understanding on how all of this works. I can like forgot the stream output there, but that's not relevant for 90% of our work. Basically allows to output the data generated by the test later, but yeah. I already was there on stopping the video. So yeah, thank you for watching. See you on the next video. Make sure to like and subscribe, and have a nice day. Bye.